and welcome back to Math 256. This is Scott. Let's get started. So what we're going to talk about today is section 4.4, in which we will be discussing forcing and resonance. So this is more or less a continuation of the same topics that we've been doing, just looking at a very specific phenomenon that happens in a specific category of examples. So let's talk about our setup. What we're going to have here is an undamped harmonic oscillator. And in particular, the equation that we'll be using will have the form x double prime plus omega squared x equals f of t. And here, specifically, when we look at this category of equations, we're going to end up with some commonalities and some differences. So here, specifically, notice I have written this constant here as omega squared, and that indicates two things. Number one, this whole term is going to have to be positive. Number two, that there's some meaning to the omega squared, or just to the omega naught. So first off, let's look at the homogeneous version of this. So the homogeneous version, which is the version that has no forcing. So it's unforced. So then, if we look at that, we're going to have r squared plus omega naught squared equals 0. And this is a constant. So then that means r squared is going to equal negative omega naught squared, which means that r is going to equal the square root of that, which is going to be plus or minus omega naught I. So then the solutions will have the form x equals c1 cosine omega naught t plus c2 sine omega naught t. So these will be just perfectly periodic sinusoidal functions. So these, I would call it xc for the complementary solution here. So these are periodic, in particular, with period t equals 2 pi over omega naught. Sinusoidal functions. Omega naught is called the natural frequency. So this is the term used by your book. So in reality, it's not frequency in the sense that we would typically think of it. Frequency you think of as being the number of times something happens, but in reality, it's scaled a little bit. So in reality, it would be omega naught over 2 pi would be frequency in the usual sense that we think of it, but this is fine for us. Now, So the forced version. In particular, let's say that f of t is a sinusoidal function. So sine or cosine, it doesn't really matter. They're basically two sides of the same coin. So for example, f of t equals sine of some omega t. This is not omega naught, just some other omega t. Now, case 1. Omega is not the same as our omega naught. Then, our particular solution will be periodic with frequency omega. Then together with the complementary solution overall solution x of t will be made up of two interfering sinusoidal patterns. And the graph will look like this. So here, what's going to happen is, and it's easiest in drawing it, if I draw what's called the envelope function first, just to help. So draw yourself a big sinusoidal function, big overarching one. And then draw its reflection down here. Just a big picture. You want a good picture? You can go to your textbook. It's got some compelling graphs, or we're about to look at some on Desmos. And what you see inside here is sinusoidal, and what we have around here is what's called the envelope function. Around the outside. And on the inside, what we have is a sinusoidal pattern with increasing and decreasing amplitude. All right, so that's case 1, where the omegas are different from each other. Case 2, omega equals omega naught. Well, in this case, we can't solve it by using like the untampered with methods that we have seen for undetermined coefficients. We need to include a t. So the periodic solutions I should say the particular solutions. I should say particular. The particular solutions will involve an extra factor of t. And the effect of this extra factor of t is called resonance. This causes resonance. And the solution will be a pseudo-periodic function. And by pseudo-periodic, I mean that it looks periodic, but in fact it's not because the values aren't exactly repeating, with increasing amplitude. So in particular now, the envelope function is just going to be something like this. And you just get a sine wave that's just going up and up and up in its amplitude, and its swings get more and more wild. This is the phenomenon, by the way, that causes famous engineering disasters such as the Tacoma Narrows Bridge in Washington, where a bridge was built seemingly perfectly sound, but it just so happened that the natural frequency of the bridge as constructed happened to match the what ordinary amounts of wind would cause for extra vibration, and so the vibrations the vibrations would then amplify each other, and the bridge would oscillate wildly, and then eventually it actually came apart. The same thing happened with a bridge in England, in Manchester, when some soldiers were marching over it, and a very similar thing happened with the Millennium Bridge in London that they built for the year 2000. So this is a pretty common phenomenon, and this is one of the things that actually intuitively we know without even knowing that we know it. If you have to move a heavy object, you'll try to rock it back and forth in order to move it. Why do you do that? Because you're trying to induce some resonance in order to amplify the effect of what is otherwise not going to be a sufficient force. So let's take a look at some examples of some equations that fit this pattern, and we'll see, or one or the other of these patterns, and we'll try to determine what exactly is going on, and then we'll go over and take a look at some graphs of these things as well. So examples, and here what we're going to do is solve some initial value problems. And then while we're at it, we'll answer the question, is there resonance or beats? Basically one or the other in these cases where we have this category of differential equations. But let's have a look. All right. First one, let's just say something like this. I'm going to say y double prime. So we're going to use y's or x's, either one, plus y is equal to sine t, and we will just say y of 0 equals 0, and y prime of 0 equals 0. So this is going to be a system that is initially at rest at its equilibrium. So if we think about it as a spring, it is not starting off being stretched, and it is not in motion at the exact moment that we take a look at it. But it is being forced by a forcing function of sine t. Okay, well, let's just solve this by regular means. Now let's just go ahead and complexify it to begin with, since we have that tool in our arsenal. So y double prime plus y is equal to e to the it, and we want the imaginary part. Okay, so let's start with the complementary solution. So we have r squared plus 1 equals 0, which means that r equals plus or minus I. Uh-oh. So y complementary is equal to c1 cosine t plus c2 sine t, which steps right on the toes of what we were going to use as our particular solution. So for the y particular, first draft, we tried a e to the it, but there's a duplication. Okay, well, if that's not going to work, then what? So we'll try draft 2. A t e to the it. And so we'll give this one a try. So then the complexified version here, if we take the derivative, it's again going to be a question of the product rule. So it's going to be a e to the it plus I a e to the it. And then if we take the second derivative, we'll have I a e to the it plus, oh, sorry, I'm missing a t here. T. So plus I a e to the it plus I squared, so it's going to make it a minus a t e to the it. So what is that? That's 2I a e to the it minus a t e to the it. Okay, so now we've, nope, see, this is what happens. I change letters and I forget that I changed the letters. So these are all y's, of course, not x's. Okay, so then y co double prime plus y co is supposed to equal e to the it, but by our investigation over here, if there's a mystery a, it will fit in this pattern. 2ia e to the it minus a t e to the it plus a t e to the it is equal to e to the it. I can cancel the thing that is shared by them all. That's the e to the it part, and also I notice that this is going to cancel that. And so I get 2ia equals 1. All right, well then a equals 1 over 2I. Multiply top and bottom by the conjugate, negative 2I. Negative 2I over positive 4 equals negative 1/2 I. Okay, well then A t e to the I t, which is our final draft of our complementary solution there, is going to be negative 1/2 I times t times cosine of t plus I sine of t, which is going to just equal, if we break it into its parts, negative 1/2 I t cosine t plus 1/2 t sine t, and that's going to equal then. So for the, so this is going to be the imaginary part. And this is going to be the real part. This is what we wanted. So we're going to run with it. So our y p is going to equal negative 1/2 t cosine t. Okay. Well, there we have it. Now, that means that our y is equal to c1 cosine t plus c2 sine t minus 1/2 t cosine t, which, if I want to plug in the initial conditions, I'm going to need to have not just this, but the derivative of this. So then y prime is equal to negative c1 sine t plus c2 cosine t. Here I'm going to need to use the product rule, so minus 1/2 cosine t, and then 1/2 t, and it would be negative sine t, but that cancels the negative that was in front, so that becomes positive sine t. And then I plug in the initial conditions. So y of 0 equals 0, y prime of 0 also equals 0. And what does that lead us to? That leads us to 0 equals c1 plus 0 minus 0. Okay, duly noted. c1 equals 0. As for this one, y prime, 0 equals negative c1. It's not going to be anything. We're going to have c2 minus 1/2 plus 0. So then c2 equals 1/2. So what is that going to leave us as our overall function? It looks like our overall solution here is going to be y is going to equal, so c1 was equal to 0, so we're going to have 1/2 sine of t minus 1/2 t cosine of t. Okay. This has resonance. And we'll see what that looks like. We'll see a graph of it just in a moment. Well, not just a graph of it, but even an animation of it. All right, so that's one. Let's try another one. So let's go with something like this. Y double prime plus 9y is equal to cosine 2t. All right. Well, here we go again. Let's complexify this. So it's going to be y double prime plus 9y is equal to e to the 2it. And here we're going to want the real part. Okay, now let's start with the complementary solution. So r squared plus 9 equals 0. So r equals plus or minus, so subtract the 9 to take the square root, so 3i, which gives us a complementary solution of c1 cosine 3t plus c2 sine 3t. Alright, well I feel pretty good about that now because we're not going to be duplicating. So the y complex here, this is going to be a e to the 2it. So that's good, no duplication, so I can proceed according to my usual patterns. So then 2ia e to the 2it will be the first derivative, and the second derivative will be now negative 4a e to the 2it. All right. It's all well and good, and then we put it into the original equation. So we're going to have 9 YCO equal, and by original equation I mean the complexified equation. So then we're going to have negative 4a e to the 2it plus 9a e to the 2it equal to e to the 2it. And what's this going to give us? It looks like we're going to have 5a e to the 2it equals e to the 2it. And so we're just going to get a equals 1/5. Interesting. And so then what that means is a e to the 2it is going to be 1/5. So no, there is no imaginary part here. Interesting to note. And then we're going to have the cosine 2t plus I sine 2t. So that's just going to be 1/5 cosine 2t plus I over 5 sine 2t. And we want the real. So then that means that our particular solution is just going to be that 1/5 cosine 2t. Okay, well then, what does that leave us for our overall y? It's the combination of those two. C1, cosine 3t plus C2 sine 3t plus 1/5 cosine 2t. Oh, I forgot to give us some initial conditions. How about the initial conditions here are the same as before. Y0 equals 0, y prime of 0 equals 0 as well. Okay. Well, to implement these initial conditions, I'll need the y prime, so here we go. So it's going to be minus 3 c1 sine 3t. This is going to be plus 3 c2 cosine 3t plus, minus 2/5 sine 2t. And now, since we're talking about initial conditions and finding the solution that fits them, we'll just plug those in. So remember, the initial conditions were y of 0 equals 0, y prime of 0 also equals 0. And so that's going to lead us to 0 equals c1 plus 1/5. All right. Remember, when it comes to sines and cosines, cosine of 0 equals 1, sine of 0 equals 0. And then the other one is 0 equals, looks like 3c2, and that's it. So I can see that c2 is going to equal 0, and c1 is going to equal negative 1/5. And so where does that leave me? That leaves me as at y equals negative 1/5 cosine 3t plus 1/5 cosine 2t. So here what you see is a final solution that has two sinusoidal functions of different periods, and so they'll be interfering with each other. And so this is going to be causing beats. All right, well, that's enough of that. If you can do 2 examples, you can do 1,000,000 examples. The real question is, what does this all look like? So for that, we will switch over and take a look at this on Desmos. All right, now as you can see here we have Desmos, and I have taken the liberty of entering into it our first 2 functions, the 2 solutions that we just found. So let's have a look at what the graphs of these look like to begin with. So starting with f. So f was the first one that we did, and this was one that had an instance of resonance. So let's see what that looks like. So you'll notice that it is equal to 0 when t equals 0, just as the initial conditions promise, and that the derivative of it is also equal to 0 at that same point. Now, after that, so that basically represents it being at rest, but it's being forced, and it's being forced in a way that is actually resonant with its natural frequency. So what happens is we start getting more and more and more high amplitude oscillations here, and it just keeps on growing and growing and growing. So if this were, for example, something like a bridge, and the bridge had a natural frequency just based on the way it was constructed of such and such, and it just so happened that that the wind or the footfalls of soldiers happened to match that frequency, what would be happening here is that the force that was being exerted on the bridge would be amplifying over like with each oscillation. So and this is again what we naturally think of. If you tried to move a heavy object and it didn't budge, what would you do? Like just naturally, your instinct would be to try to rock it by doing a natural rhythmic pushing, and that is actually all a question of you trying to push it in harmony with its natural frequency. All right, so that was the resonance. This one is the other example. Let's have a look at what happens here. So here, what we have are beats, and you'll notice it is, so this is periodic, and unfortunately, these particular beats are not super, it's not super clear, but actually, and in some ways, it's easier to read these than it would be in many cases. So we can see that it is a repeating pattern. That much is clear. It's a repeating pattern of 2 little humps and then a big hump, and then 2 little humps and then a big hump. Now, just as a note, if these numbers were quite a bit bigger, you would see a lot more complicated of an interference pattern. So for example, so these were 3 and 2. Let's make them 13. Well, actually, that already is pretty interesting. And then 12. Oops, too much. 12. So then, sorry, I made this 33. I meant 13. So then what we have is, again, it's hard to tell because of the scaling here, but what we have is it growing and then shrinking and then growing and then shrinking. These 1/5 are really compressing it a bit. But the one that we had here, let's have a look at that. So it was 3 and 2. We have, again, a repeating pattern. It is kind of mild, then it's bigger, and it's mild again, and then it repeats. Okay, and at the origin, when t equals 0, y equals 0, and the derivative of y also equals 0. So we can see that this is consistent with our initial conditions. Okay, so that's all well and good, but let's see this actually in action. So the way you can animate this is you set up a point with an extra parameter, and here actually I'll make it f of a, just to have a thing to call it, comma, and then you give the y coordinate. So I'm just going to make this be a dot that is oscillating in and out according to function a. And here I'm just going to start according to function f. And here I'm just going to start a at 0, and I'm just going to run it out for a little while. Let's go to 10. All right, so now, and we'll probably want it to be going a little slowly here. So now let's look. So notice it okay, here we go, starting at 0. So, okay, so it was at 0, it's being forced by the forced oscillations out, but so then it comes back, but wait, those oscillations are exactly in tempo with its natural frequency. So it just keeps on getting more and more and more. Yeah, let's actually make that bigger and watch it again. So starting from 0, so it's just kind of getting pushed out, but now it's responding with its own natural frequency. And now the pushes are coming exactly on tempo. This is also very similar to what you do when you're swinging, like when you're on a swing set. The objective there on kicking your feet out is to kick it out at just the right time, so that essentially the pendulum that you're on has the same natural frequency as the rhythm with which you're kicking your feet out or leaning back, depending on which side of the swing you're on. Okay, now let's switch over to G, and now here we'll probably want to zoom in quite a bit because G has a much smaller amplitude. And and I'll probably need to change this. We'll change this to make it just equal to, no, we'll make it 10, just to start with. Okay, so what's happening here is we have a forcing function which is not quite in tempo with the natural rhythm, and so what's happening is we're like pushing against the grain sometimes, and so you're trying to rock it, but you can't get the rhythm right. And so what happens is sometimes it's going out, and sometimes you're actually dampening your own the effect of your own pushing. So it comes in, comes out, comes in, comes out. So you're trying to swing it back and forth, but you're out of rhythm with it. And so as a result, sometimes it's increasing, but sometimes it's dampening. Okay, so anyway, that's what these things look like when we go from the differential equations to the graphs. So graphically here, what we're seeing is the interference pattern of two waves on top of each other. Like for example, if I were to cut this one out, that's the wave we would see. If I were, on the other hand, to cut this one out, that's the wave we would see. We put them together, and they amplify each other sometimes, and they cancel each other out sometimes, and that's what's happening there. All right, well, that's going to do it for this installment of Math 254. Join me next time when we will move on to a new topic where we will look at what's called linearization. All right, well, till then, bye.